So in a starting 2 to 3 minutes, we start discussing like what is AC, as you already know, how the generation of AC, and so and so. So as we discussed in the last class, AC is basically alternating current, right? It is alternating current. Alternating current means a kind of a current which fluctuates or which changes its polarity time to time. Is this clear, everyone? Clear na? One basic thing, in India, the frequency of alternating current is going to be 50 hertz. In India, frequency, what is the frequency and everything for this, you're going to know about in a minute. Frequency of AC is 50 hertz. Okay, what is the meaning of saying that? Just a minute, I'm going to give you the meaning also. Whereas in USA, it is 60. In USA, United States of America, frequency of AC is 60 hertz. Meaning of saying that, like this particular, as we know, AC is going to be produced by the product, by the motion of this particular thing. You can say my moving coil galvanometer, or basically AC generator, right? So in India, this particular coil, or you can say this generator, rotates 50 times in a second. Like what is this? Frequency is basically 1 upon time period. So in 1 second, this is going to be rotated 50 times in India, this particular coil. Because the moment this particular coil rotates, and due to the rotation of this coil in a magnetic field, that is how we can produce the AC, or this is basically induced current with the help, or with the you can say with this particular process of EMI, right? Is this clear, everyone? Is this understood? In the last class we discussed this. In the last chapter we discussed this thing. But in India, frequency of AC is 50 hertz, wherein is USA means in India we make the particular generator in that such manner, like in one particular second it rotates 50 times, whereas in USA they make that particular AC generator in that such manner, so it can generate, or sorry, it can rotate 60 times in a second. That is the simple basic mean. Clear? And that is why we use 220 volt or 50 hertz AC, and in USA 240 volts or 60 hertz AC. That is the basic difference. Is this clear, everyone? Meanwhile, better please turn on their camera, or just camera, not video. Okay. So due to the rotation, as we already discussed in the previous class, this is your alternating current. Alternating current is termed as current changes. Okay, it's termed as the current that changes its magnitude and direction periodically. Often this periodic changes of direction is defined by a sinusoidal function. Basically, in general, there are two types of current. This is your alternating current. Simply understood, alternating current stands for where the magnitude and phase is going to be changed continuously. Alternating current, this one is. Okay. What is sinusoidal function? Beta, sine function. This is a sine function, na? Sine theta, or you can say sine function. Is sinusoidal function, where it is written over there, this one. Okay, clear, everyone? So sinusoidal function is nothing but sine theta. It is theta, not q. Okay, sine theta equals to sine function equals to sinusoidal function. As you can see, at 0 it is 0, or the moment it increases after a certain height or maximum point, it is going to be this and that. Okay, where the magnitude change as well as the phase change, means positive, negative, positive, negative. But in direct current, it is going to be a constant. This one is your direct current. Is this clear? Direct current. Clear, everyone? So this is your direct current. We have different types of AC as well as, this is the basic general, or you can say sine cosine function gives you the general terminology, or you can say more number of times you are going to see the sine function. Sometimes you are going to see the cosine function. Cosine function is nothing. Cosine function is cos theta. Okay. Nothing more than that. Sine function is basically, or you can say sinusoidal. Sinusoidal, or you can say sine function is in general sine theta. So that is the sine theta. But we have more different kinds of ACs also. Okay, so this is again the recall, like how we generate this Faraday's law, Faraday's principle of electromagnetic induction, E equals to minus nd phi by dt. This is your EMF. Here E is electromagnetic force, electromotive force, and number of turns, coil, this. Okay, see, we already done this, so we are not going to worry about it. So here the current generated, this current is basically a sinusoidal current, or this induced current. Okay, this induced current in general is AC, alternating current. Okay, is this clear, everyone? Okay, why do we use alternating current AC electricity? Because solar panel converts sunlight to DC, and then extra, basically the main purpose to use AC, or because whenever there is a transportation of energy, or basically electricity, so in DC there is the transportation of DC is very difficult. Why? So because there is a much power loss is going to be. Okay, because direct current, the power loss, or you can say power loss. Now what power loss is, you going to see in this chapter as well as, basically power loss P is going to be VI is going to be I square R. So if there is a direct current, okay, so in direct current, this I is going to be either average or either the maximum value. So suppose this is your a long wire in this way, okay, and you need to transport your power from one transmission, which is, you can say, thermal power plant, to the state function, or state function means to any particular another state or district. So that this transmission line is going to be about few hundred kilometers or few kilometer, for you can say, sir, where the DC current is used. But a DC current is used for a small current application. For example, like the DC current is used in our analogous clock, specifically clock on the wall, remotes, and where we can use the battery cell. That is basically DC current, direct current, right? Or in old few, you can say, heating filament, we use DC current as well, where we need to get the heating effect more in terms. But in general, nowadays we use AC current more as compared to DC current. Okay, like there is one cathode ray tube experiment, there we use DC current as well. Cathode ray tube experiment is, we need to warm up that cathode ray basically to see the I mean, you can say to see the particles of an atom in general. Okay. So where I am, yeah, suppose this A is, you can say, thermal power plant or any particular power plant or a power plant in general. Power plant, and you need to transmit this, suppose, up to only 20 kilometers. So even up to 20 kilometers, as we know, resistance is directly proportional to length. So resistance is going to be very high. Okay. and this I square, I is going to be very high. Even you convert into the V terminology, V square by R, then it is also very high. So this power is going to be lost as compared to heat, because heat energy I square RT. To transmit this particular electricity from A particular point to B particular point, any particular state or a town, okay, state or town, that requires this power loss. So the power is going to be very low, but it is not going to be happen in AC. We are going to see that if there is a maximum current is 0 to 10, so the average current I average is going to be only 70% of maximum, or you can say peak value. That is why we use AC in more number of terms. Is this clear, everyone? So this is solar panel converts sunlight to DC current. Then the extra electricity credited on grid. Take electricity your home requires inverters converts electricity DC to AC. Basically what happening, what they try to you can say make you feel in this, whenever we have extra energy, or you can say whenever there is a energy is going to be created in any particular power plant, so to transfer this particular energy from one point to another point, you lost a lot of amount of energy if we use DC. Okay, but if we use AC, which is alternating current, so the power loss is going to be very less. That is the main thing, and that is why we use AC over DC. Is this clear, everyone? Is this clear with everyone? Okay, good. This one, and then this. Okay. Now production. We know these currents can be generated using devices which are known as alternators, or you can say basically generators. Apart from these, there are many circuits that are able to produce alternating voltage and current. One of the most basic way to produce an AC voltage or current by using single coil AC generator. The generator consists of two pole magnets and a single loop of wire which has a rectangular shape. Okay. Now this is important. Now frame, till now we are doing the recall thing and everything. There are different types of AC. Pure alternating EMF is sinusoidal. Pure AC is sinusoidal. What is the meaning of pure? Means in generally whatever the 1, 2, 3, 4, then 5, and 6, and 7. We have these different kinds of AC. You can say first one is, you can say first two are almost different. Pure alternating EMF. This is EMF means electromotive force, or you can say sinusoidal voltage. This is your alternating current or a sinusoidal. Now what it is? Alternating current of a rectangular. The main basic thing for any particular alternating current at a certain time interval, okay, after a fixed interval, after a fixed time interval, after a fixed time interval, the phase of alternating voltage or alternating voltage or current is going to be changed. That is the main thing. Current is going to be repeated or changed. Is this clear? So as you can see, in different kinds of alternating EMF or current, this is going to be repeat its cycle after a fixed interval of time. Suppose it starts from this 0, going higher, coming back to the 0, then negative higher, and then 0, and then it starts repeating itself. In a same sense, it is a current. In a same sense, maximum at the initial, or you can say at 0 time interval, it is going to be maximum, then this suddenly to the negative maximum, then negative, and then maximum. Then again same cycle repeating. Here we have this kind of alternating current is known as sawtooth, going from negative to 0, then positive maximum, then suddenly negative. This function is known as direct delta function, but suddenly, or you can say rapidly, going to again, then again, then again. In this way is a triangular wave. Very simple. It forms a triangle, so it is known as a triangle wave, going from 0 to maximum point at a linear, then coming back to the 0 as a negative linear, then from 0 to negative maximum linear, and then again this cycle, and then the cycle repeats. Here it is asymmetrical, like it is going to be constant for a particular time, then suddenly decreases to the negative maximum, then increases in a linear way, and then repeating its cycle. It is the current generated by your full wave rectifier, or you can say ripples. These also known as ripples AC or alternating ripples. This is basically alternating ripples. Okay. In the semiconductor chapter, then we are going to discuss about diode. So there is a application of diode, full wave rectifier, half wave rectifier. Basically what this particular do, the process to convert AC into DC is going to be done, and this is one kind of alternating current in which you have only one phase, but this is known as ripples. What basically that particular diode does, as we have seen, this is your negative cycle, okay, and then it is going to be positive. There are two different, okay, wait a while, then you are going to understand. There is one of the cycle is this cycle, okay, so it is going to be in this way, and another cycle is obviously the upper cycle, that is going to be in this way. So what is the application of this full wave rectifier? It, you can say, clip out the one phase, the negative phase in general, negative phase, or you can say negative cycle is going to be clipped out. As you can see, this is clipping out from the black part or even from the green part. This is clipping out, okay. From here it is clipping out and you only see the upper part. So that is alternating ripples generated from full wave rectifier. Oh, I can write it down here. Generated from full wave rectifier. So right now it is enough to know about it. Okay, what is a full wave rectifier? Nothing but it is a circuit containing two diodes in which we need only one kind of, you can say, either positive, either negative DC. Obviously, there is a one more, there is a simple process to convert AC into DC, and this is the intermediate process. After this, we are going to apply one more circuit known as RC circuit. Then after RC circuit, how it is going to be visualized in this way. Okay, so these are small ripples, and the small ripples basically in this way. So this small, you can say fluctuating, almost behave like a DC. So that is the process of converting AC into DC. In the same fashion, we are doing with this. Okay, for alternating, you can say either sawtooth alternating is going to be converted into this DC. This is half AC, or you can say only one phase of AC. Is this clear, everyone? Clear, everyone? Shrutika, Netra, Yajira, and Parikshit, Sushita, or everyone, please turn on your cameras too. Okay, clear na? Good. Yeah. So this is your important terms, and In more than important terms, I think I need to teach you something more important. I'm going to. So let's discuss this, and I am then starting because it is not given in this. So important terms: cycle of alternating EMF or current. The variation. First of all, you read this, and then whatever the important thing I'm going to teach you. The cycle of alternating EMF and current. The variation of EMF. The variation of EMF from 0 to maximum in one direction through 0 to maximum in opposite direction and back to 0 again is called a cycle of alternating EMF. Basically this thing. Okay, basically this thing. It is going from 0 to it is going from 0 to maximum. This is your maximum point, 0 to maximum, then maximum to 0 again, okay, and then 0 to negative maximum and then 0 again. So this complete one cycle is known as a cycle of, and the time duration to take this particular complete cycle is known as time period. Time duration to complete one cycle in our AC is known as time period. Okay. In the previous, in class 11, whenever we learn about this particular thing, which is you can say waves, right? EM waves, electromagnetic waves, or simple waves and ripples. Then we learned these kind of terminology like time period, frequency, maximum value, minimum value. So this particular maximum value is basically known as peak value also. Peak value or maximum value. Is this clear now? And peak value is generally defined by I naught or E naught. Is this clear, everyone? Okay. I naught or E naught. Okay. More than that, yeah. So important terms: period and frequency of alternating EMF or current. Alternating EMF is defined by the equation. This is your important equation first, and that is why we have a sinusoidal. As you can see, EMF, or you can say alternating EMF. This is your alternating EMF. Equation 1 shows you alternating EMF, which is E naught sin omega t. Beta E naught is this value. This is your E naught value. Okay, this one. Where should I write? So this value is basically E naught, peak value in general. Clear? So this shows that after a time interval of 2 pi upon omega, this T, alternating EMF or current repeats its nature. What is this 2 pi by omega? Omega is basically an angular frequency. Omega is 2 pi by T. So after this particular time interval, which is 2 pi by omega, okay, here omega is angular frequency. What is angular frequency? Angular frequency, you can say angular velocity, you can say angular frequency. Angular frequency is beta is in general like how much it is going to rotate. How we basically generate this alternating EMF or voltage by the rotation of a coil, right? Is this clear na? In AC generator we see that by the rotation of this particular coil. So how much speed it is going to rotate, that is your omega. Omega is in general angular velocity. For AC generator or for this particular cycle thing, it is angular frequency. Nothing more than that. 1 by T is F. So that is 2 pi by F. I teach you this thing even in the last class also. When I give you XL. XL is omega L. Omega L is angular frequency or angular velocity. 2 pi F. Clear? Time taken by the alternating EMF or current to complete one cycle or its variation. Time interval 2 pi by omega is called the time period of alternating EMF or current. Is this clear, everyone? Is this clear now? Are you there? Yes, she is. She is also. She is also. Is this clear, everyone? Good. Now, frequency number of cycles completed by alternating current or EMF in 1 second. Frequency f equals to 1 by t, but t equals to 2 by 2 pi upon omega. So frequency is equals to omega upon 2 pi, or you can write it down. This is angular frequency also, 2 pi. Just rearranging the terms. Units of frequency, that is cycle per second or hertz. In India, frequency of AC is this. In America, it is 60 hertz. I already give you this thing. Before this, 2-3 important things I am going to discuss here. And okay, let's choose the previous page, because previous page is not, as such written over there. So from this particular page, on few things on next page. Types of AC, or you can say different forms of alternating current, and that is very important. Different forms of alternating current. Alternating current. Okay. In alternating current, if in general we are going to find the average, so average alternating current is going to be 0 in general. Why so? Okay, first of all, different form, or you can say this is not going to be one. Okay, basically we are going to talk about average or R.M.S value of alternating current. Directly I am going to average or R.M.S. R.M.S stands for root mean square. Root mean means under root. We are going to square of these current, then we are going to take the mean and then the root, basically. Average or R.M.S values, or you can say value of AC, and that is very, very important. I don't know why in this particular PPT. I think it is in the next, but I feel you need to know here. That's why I'm teaching you. Okay. So first of all, anyone please tell me what you expect the average value. Average value of AC. According to you, a guess, average value of AC. Obviously, I am going to tell you, know na everyone, what is the average? If you have n numbers, or you can say n different values, so sum of n different values and add it down. So we have this particular AC. Okay. We everyone know this is my alternating current look like. And this is, in the same way, I can write I equals to I naught sine omega t. Clear? We can write it down. So now you tell me, this is your I naught, this is your I, and here we have to represent time interval t. Clear? So now you tell me what is the average value of this particular AC, alternating current. Anyone? Tell me, anyone? Yajira, Kyle, and this Parikshit, Sushita, Vishwanath. Is this done in your school or somewhere? You can say the mean or average value. Mean you also can say that.
Hello, Nitin sir.
Yes.
Nitin sir.
Yes.
Sorry to disturb you. Actually, Kyle Netra.
Hmm.
Are you using a mobile or something else?
Laptop.
No, no. In hand. You are
While
using
you
mobile.
are, in this particular class, so I think, they should see, yeah. I mean, are you using something else other than laptop? No, sir, I have my class. I was searching. Better so do one thing, because in this way, neither you are focusing on your classwork, neither here. Correct?
Actually, you should pay attention in the
Yeah,
class.
that is the main,
This
you
is for
can say.
everyone.
Yeah,
Okay. Yeah. Sorry, sir. Thank you, sir.
it's okay. Thank you, sir. Okay, so average value, or you can say mean value. Tell me anyone, please. We are running out of time. I mean, time is running and we need to go through so many things. Okay, basically, as you can see, it is a positive, because I think it takes time, and positive, negative, and so, right? So it is going to be zero, obviously. But we don't have, I mean, we use alternating current in day-to-day life. So how it is going to be work then? In your home, right now we are, you can say, taking this live lesson because of electricity. If there is no electricity, so we are not able to take that. So how it is working then? Have you thought of? So first of all, the correct answer is, I mean, Parikshit gives us the correct answer. For complete cycle, for complete one cycle, for complete one cycle, the mean value, whether you can say the average or mean value of AC is zero. Correct? Because it is positive, negative, positive, negative, positive, negative. So in any particular sense, we are going to do that. It is the particular zero. So what we are going to define, we are going to define something else. The mean value, the mean or average value of AC alternating current, we are defining define DEFI, and I am defining for half cycle. Okay, because for half cycle it is always positive. As you can see, for half cycle, and it is going to be positive. This positive, this, and that. Okay, half cycle. So obviously it is a continuous thing, and for continuous, you can say, values, or for continuous quantities, the average or mean value is basically nothing but 0 to t by 2, because it is a half cycle. Is this clear? Okay. I T dt. I T dt is basically how much, I mean, for how much time you are going to observe, and IT is I, because it is dependent on time t. Clear? Okay. So the moment we are doing this particular integration, putting value of IT or simply I, AC, so 0 to t by 2, I naught sine omega t dt. Clear, everyone? Okay. Because I naught is a constant, it is a maximum value. So I average is nothing but I naught, and sine omega t dt. Okay. Dt. This particular integration is, I mean, this is my equation number 1. Because 0 to t by 2 is there. So this is my equation, or you can say equation number 2 is used to find average or mean value. And it is simple. I average is nothing but I naught. Okay. It is going to be cos omega t divided by omega, and this is the integration, and 0 to t by 2. Clear? Where we know this thing, omega is nothing but 2 pi by t. Clear na, everyone? So I can do that. I naught upon omega, here I can put first of all, and then you can see here cos 2 upon 2 pi into t. Instead of t, I can put t by 2. Clear? Is this clear, everyone? Clear na? and minus uh, it is going to be cos of 0. Cos of 0 going to give you 1. Sin omega t is give me minus cos omega t or cos omega t. Okay, we can do that mode then. So I average in general is I naught upon omega, and it is t by 2, pi by 2 or cos pi. Okay, that is cos pi, and that is minus of cos 0 degree. So from here, that is 1, minus of 1, and that is 1 also. So I can get I average is 2 I naught upon omega if I do the mod. Okay, and if I'm not wrong, the integration of this sin omega t is going to be minus of cos omega t. Sin omega t is, yeah, minus of cos omega t. Okay, and that is why you are not necessary to do the mod also. This is minus of cos omega t minus, and we took minus here. So taking minus, how I am doing that? Minus I naught upon omega. It is minus 1, because cos pi, which is cos 180 degrees, minus 1, and minus 1 cos 0 is 1 only. So this is your average value. Okay, and if you put the value of omega also, which is 2 pi by t, so it is going to give I average using this. I average, either you can use this directly, or I average or mean is 2 I naught upon 2 pi upon t, which is 2 cancel, and what is the value then? You can get 2 I naught upon, wait, 0 to t by 2. It is going to be 2 I naught by pi, where we are doing mistake, putting the value of 2 by t. Okay. Yeah, I have one omega here as well. No? Omega is okay. See, here this particular t is 2 by t by 2, not completely. Okay, this omega is going to be for t by 2. So the main thing we are going to get here 2 I naught upon pi. This is not t, this is t by 2. So this t by 2 cancel with each other, and that is your thing. Is this clear, everyone? Here the time period we are calculating, we are taking half cycle. So the main thing is the average value you are going to get either this is, you can write prime also. Why should I write prime? Because omega prime is for half value. In this way you can understand, which is pi by t also. 2 pi upon t upon 2. So yeah, pi by 2. Okay, and then you can get this. 2 I naught by 5. So this is your value. Is this clear, everyone? Wait. I need to remove this. So this is. So this is my average value. Clear now, everyone? Either you can say mean value, or either you can say average value. So it is going to be proved for same volt. You can write e.m.f, and in the same way for, you can say, current. So for current or e.m.f, the mean or average value is going to be 0.637 I naught, which is 7%, or you can say 70%. So I tell you this thing now, like in the same sense, I mean or average is basically 0.637 of I naught, and if you are doing the percentage wise, so it is something 63.7, approximately 70% of total value I naught, maximum value. What is the meaning of this? Suppose there is a current 0 to 10 ampere. Okay, so the average current or mean current you are going in as compared to AC, for AC this much only. In the same way, EM or EMF mean, or you can say mean EMF or average EMF, is going to be 0.637 of E naught. Is this clear, everyone? This is clear, na? E naught or I naught is the maximum peak value. M or average is the mean or average value. And even mean or average value we cannot find for the complete cycle. Clear? Now the another important term is going to be R.M.S. And what is R.M.S? Let's discuss this also. So in the previous page we are discussing the average value or mean value for alternating current or alternating EMF. Here we are going to root mean square. Root mean square. Okay, why we need this root mean square? Value of AC. Anyone? Why we need this? Tell me, anyone. Why we need this R.M.S value or average value? When we already define this average value, then what is the use of R.M.S? The simple use of R.M.S, as we know, suppose, okay, why we are discussing this? See here. Suppose there is a resistance, right? And there is my alternating voltage. Clear? This is your V equals to V naught sin omega t. I'm going to erase this. And this is my just clear. This is my circuit. This is my resistance. This is the resistance R is going to be, and this is your AC voltage, alternating voltage. So here the current is going to be fluctuated as compared to the AC, and for a very small time, your I, or you can say DI current, DI current is going to be I naught sin omega t dt. Di by dt. dt. Is this clear? Or no? Di is going to be dq by dt. This is clear, na? And where dq is very small charge, you can say generated due to this induced voltage. Clear? For very small time. Now there is a fluctuation of time, and there is a you can say fluctuation of voltage is going to be very high, because in 1 second you can see 50 hertz. Okay, 50 hertz. 50 hertz is the voltage, frequency of a AC. So in 1 second it is going to be rotated in this way. So if you need to find any particular time, so again the average value for complete cycle is going to give you 0, but we know it for complete cycle. So for that purpose, we find R.M.S value, root mean square value. First of all, what is R.M.S value? Suppose you are need to find this, you can say R.M.S. First of all, whatever it is, suppose this is at one particular time, it is this, then this, then this. Only we are interested in 3. So I.R.M.S in general, it is somehow one of the basic thing to get more accurate average value. Clear, everyone? Then you are going to see, we are going to find the relation between I.R.M.S and peak value again. Is this clear? The root mean square value of alternating current is defined as the value of a steady current. Steady current which would generate the same amount of heat in a given resistance. in a given time, and it is represented by this. It is also called the effective value or virtual value of alternating current. The emitter, when connected in the circuit, always measures R.M.S value of AC, nothing more than that. Is this clear? Or in a proper definition, you can see this. I mean, whatever I am reading, I can give you also. So this is your, and for this value, we can find R.M.S. Okay. So this is the definition and important thing for R.M.S. Nothing more than that. If you want to write the definition, but in general, it is this. Clear? Like if you try to convert this AC into steady voltage, steady current, so that is your R.M.S. And whatever the heat, whatever any particular other quantity related to this current, we are going to get, we are going, we are using this I.R.M.S. This is I.R.M.S. value, root mean square, and that is your actual AC. And that is why it is also known as virtual value of alternating current. Is this clear, everyone? So simply what we are going to do, I.R.M.S. is nothing better, but it is again the how you going to get the you can say average or I.R.M.S. is square of this thing and 1 by t 0 to 2 I square dt, because it is a continuous thing. So to get this, to get this equation, what I'm going to do, this is your first equation. Okay. So if I'm squaring both the sides, we can say square is, so I square R.M.S. it is I1 square plus I2 square plus I3 square plus so and so I n square divided by n. And what it is it your average value, isn't it? But average value of square current, not simple current. And why we are doing this square? Because the moment you do the square, you can get the, in the previous page I am teaching you I average or I mean only for half cycle, because for full cycle it is 0. Very clear, very easy understanding. Clear this thing? But obviously we need to find the full cycle now. So to find the full cycle, I am doing the square, and the moment I do the square, this negative cycle, okay, wait for a while, this negative cycle of mine, or this negative cycle of this AC is going to be converted into positive heat. Clear? So for that we are using I.R.M.S. value, and obviously it is a continuous thing. So instead of summation, what we are going to do, I square R.M.S. is nothing but 1 upon time period 0 to t I square dt. Clear, everyone? Clear? And why should I require this? Because I need to find the average or steady current for complete cycle also. 1 upon time 0 to t I square, which is I naught square sine square omega t dt. Now better you cannot find the integration of this. So what we are going to do then? We are going to put the value, which is 2 sine square omega t equals to, or basically the formula is cos 2 omega t is 1 minus 2 sine square omega t. That is your formula in mathematics, or you can say in trigonometry. So 2 sine square omega t is nothing but 1 minus cos 2 omega t. Omega t you can put theta also, and then sine square omega t we can get 1 by 2 1 minus cos 2 omega t. So I am going to put this in equation number 2. This is my equation number 2. So R.M.S. okay, 1 upon t and then 0 to t, instead of I naught is going to take common I naught square and then sin square, instead of sin square t, I am going to put 1 by 2, 1 minus cos 2 omega t, and that is dt again. Okay, then it is very easy after this. I square R.M.S. Now it is integration only. I square upon 2t, and it is going to be small t minus sine 2 omega t divided by 2 omega, and then 0 to capital T. The moment you put capital T and value of omega, omega value is 2 pi by t into t. So sine 2 pi, sine n pi, sine 3 pi, sine 4 pi is going to give you 0. So from here we get only I square 2t t minus 0. Okay, t minus 0. I mean, when I put the value for this first term, when I put the value for second term, I get the 0. You can check it out by yourself. Minus, or you can do that here also, sine 2 pi by t into t divided by 2 into 2 pi by t. T cancel, and that becomes sine 2 pi minus 0. So sine 0 and divided by 2 pi. So now you can see this term is 0, this term is 0. So basically I square R.M.S. is nothing but I naught square upon 2t into t, which is I naught square upon 2. Or in general, I square R.M.S. is nothing but I naught square upon 2. So from here, I.R.M.S. is nothing but I naught divided by root 2. Clear? This is clear na? And that is very, very important. Not only for numerical problem, but this is for theoretical aspect also. I don't know why in this particular session they don't add, but I know what is not here, so I can do that. If you have any question, query till now, you can ask me. After that, it is going to be very easy because everything is written on the paper. I mean, in a PDF form, in a note. Tell me, clear na? If you are good enough in integration, so then it is very easy. Physics wise, concept wise, first of all, we define mean or average value with respect to maximum peak value for half cycle. But obviously, we don't have half cycle, we have complete cycle. So to understand the heat energy or any other aspect of AC as compared to DC, we require I.R.M.S. value. Or in any particular instrument, like it is written over there now, 16 ampere or 13 ampere for any particular AC component or AC thing. So that is your R.M.S. value. Means root mean square value. Because obviously we know AC thing, or you can say alternating current, is going to be positive, negative, positive, negative. So over the time period, it is going to give me or going to give us 0 value. But we don't have 0, we have something. So that is how we have something. The moment I square my current, automatically I don't take care, I don't need to take care about positive or negative stuff then. Because making a square, obviously positive square gives me positive, negative square also gives me positive. And then I get the total average value for complete cycle. And that is very, very important. Is this clear, everyone? Okay. Now what we are going to discuss, like if we are connecting this voltage or EMF with the resistance only, capacitance only, conductance only. And there is a phase difference also. So let's see this. Alternating current applied to resistor only. So this is alternating voltage. Okay, alternating voltage is again this. E is going to be E naught sine omega t, and then an alternating voltage source is shown. It is big N applied to a resistor. It is connected in series with a source. Thus, then this sinusoidally varying average voltage, or you can say alternating voltage. AV is alternating voltage, can be expressed by the equation V equals to Vm sin omega t. Either you can write this, either you can write this. It's your choice, whatever particular thing you write it down. So this is simple thing. Okay. Now for calculating the value of the current, Kirchhoff's law can be used. As we know, in this particular circuit, the net voltage, or you can say if I am doing this, so the summation of net voltage is going to give me 0. Applying this law to the circuit shown below, or you can just show over, V equals to IR plus 0, Vm sin omega t plus IR 0. So I basically Vm upon R sin omega t. The amplitude of this current is given by this. So this I naught, okay, I naught is nothing but minus of Vm by R. This is my I naught. Okay, moving ahead, alternating current, as you can see, applied to a resistor. Whenever I applied alternating current to the resistor, so it is Vm by R in general. And if I put the value of Vm, so I, which is Vm upon R, okay, Vm sin omega t upon R. So what I can see that I is I naught sin omega t. So the main 2 points I can note it down from here. In resistor circuit only, or when alternating voltage AV, this is alternating voltage, is passes through resistor only, resistor, and passes through resistor, passes through resistor, not this color, then phase between I AC alternating current or voltage, or you can say alternating voltage VAV, is remains same. Now what is phase here? You are going to see, and I mean in a pictorial way, remains same. But mathematically, as you can see, this is your equation number 1 for current. 1 is not A, and for voltage we have this equation. Is this clear? Okay. In both the current or voltage, I have sin omega t. The phase is same. I mean this sin omega t you have. So what is the meaning of this? The phase is not changed. And what is phase basically? As you can see, if it is converting its shape, it is changing its value after this much time. Okay, after this much angle basically. So that is going to be meet here also. The main thing is I.M., or you can say the peak value of voltage, or you can say alternating voltage or alternating current is different, but phase remains same. What is phase in general? Remains the same. But a phase is, as we know, cos theta. We can write it down. How we can write it down? Sine pi by 2 and something. Sine pi by 2 minus theta is cos theta. This is your one sense, na? Huh. Okay. Because cos 30 is equal to cos 60 degree. Sine 60 degree. When you go through the table of sine, cosine, you can get it. Cos theta equals to sine pi by 2 minus theta. And from even this triangle stimulation, you can get it. Because this sine cos is going to be for right angle triangle. So if it is my right angle triangle ABC, you can say for right any particular right angle triangle ABC, if it is theta, okay, so this is perpendicular, this is base, and hypotenuse to the base same. So cos theta is what? Base upon pi, base upon hypotenuse. Okay, so this angle is pi by 2 minus theta, isn't it? Because this is pi by 2 and the sum of all the three angle is pi, you can say 360 degree. So pi by 2 cancel out and pi by 2 is basically 90. So for this particular angle, this becomes perpendicular and this becomes hypotenuse. So sine pi by 2 minus theta is nothing but base upon hypotenuse. So that is why I do this. Okay. Did you remember this terminology or not? So what is phase here in general physical terminology? When we are apply this alternating current to inductor or capacitor, my current behaves in a sinusoidal way, or you can see that. Okay, wait. Power dissipation. After the, I mean, in a few minutes you are going to see for, okay, I'll draw and then I remove for this particular thing, like even for this, you can say inductor. When I'm going to apply this alternating current into the inductor, so in this way, my current behaves. What is this meaning? Voltage behave as a sinusoidal and current behave as a, and then this current behaving as this particular thing which is you can say cos theta. So the phase between both of them is 90 degree. They are changing the phase, they are fluctuating 90 degree to each other, and the angle between both of them, alternating voltage or alternating this current, is known as phase angle. Is this clear, everyone? Is this clear, beta? In more great detail we are going to discuss phase, but after this particular small break of 5 to 10 minutes. Meanwhile you can read this. This is nothing, power dissipation. Like I mean we discussed this thing on a very first page in a real life connect, like why it is so, I mean we use AC because power dissipation is going to be less and power average is going to be this, and I mean when we're going to put the value of average or mean value, so you can see that the power rating or power dissipation means power loss is going to be less as compared to the DC thing. Okay, so read this thing. This particular, when we apply this alternating current or sorry alternating voltage to the inductor or capacitance in this particular session itself, then you are going to more clear about the phase thing. What is a phase? In general, phase is nothing but the angle, but the change in between voltage or current, the manner they are behaving, the manner they are fluctuating. If it is, if sine, I mean current is having the sine value, so voltage having a cos value. If voltage having a cos value, so this particular current having a sine value for inductor or capacitor, and that is a phase in between. Okay, so let's take a lot you learn in this, and then after a break we are going to discuss. Hello, hello, hello. I'm audible, beta. Hello, hello, hello. Are you there, everyone? Hello, hello, hello. Okay. So power dissipation is even though the average current through the cycle is zero, but that does not mean the average power dissipation through the cycle is zero. Because I square gives you some value im sine square omega t and so and so. Means when we connect alternating voltage through a resistor, sir, what is the main chapter in 11 has most weightage in G? Beta, I can teach you. I mean, I can tell you after this if the time remaining, and if it is not, in the next class. Okay. Yeah. So even to the average, yeah, where I was, yeah. So as we already seen that like average value gives me 0 for complete cycle, and we find the solution to find the average value or to find the steady value, which is you can say I.R.M.S value, and the I mean value or average value we can calculate it only for half cycle. So power dissipation is the average current through the cycle is 0, I mean complete cycle, but that does not mean the average power dissipation through the cycle is 0. I mean it is not going to give you the 0 power dissipation. It is not like you not get any particular power dissipated or power loss. Power dissipated in general is also a power loss also. Okay. Yeah. Dissipation of electrical energy is there. It is known that Joule's heating is given by I square R and depends on I. Basically, power is E energy upon time, right? And this energy is nothing but Joule's heating energy, I square R T. So from there we get this term. First of all, I square R, or simply power P equals to VI, putting the value of V, I R, I square R. So I square is I m sine square, or I mean sine omega t square. Doing this, putting the value of this I, nothing more than that. Now, this is the instantaneous power in the circuit. Average power dissipation is given by 1 by 2. Again, why we put 1 by 2 value? Because average value is for half cycle only. I am, or you can see that average value for, okay, one thing you noted down, average value for sine square theta or cos square theta is 1 by 2, and we can see here, okay, not here in general, not here in general, here as you can see I find the wait for R.M.S. okay, after calculating every step, after doing the integration and so and so, I square t, in this I square what we are basically doing, I mean sine square thing. As you can see, this is sine square omega t, because I naught is taken out. So this is the average value for sine square theta, or you can say sine square omega t. Is this clear, everyone? Better turn on your cameras to everyone. So basically at the end what we can get, t by 2, because the limit is 0 to t. Clear? So for theta value, the average value for cos square theta and sin square theta is half, and that is why I directly put half here. 1 by 2 I m square r. I m square r is nothing but Vm square 2r, expressing this expression of power similar to usual expression. P average is nothing but I capital square R V square, I mean V capital square by R, where I capital is I m by root 2 Vm by root 2. Okay, and that is I capital V capital I.R.M.S value V.R.M.S value. Is this clear? For I m, which is the maximum or peak value, here I am not mean, it is maximum or peak value. Peak value. What I took, I naught. Is this clear? So the moment we put the I.R.M.S value, I.R.M.S is what, beta? Nothing but I m by root 2, either you can write it down, or I naught by root 2. So in a simple way, we can get the power average, which is I square R.M.S by R, and that is why use I mean, that is why we calculate the RMS value or value for this particular current or for the same particular thing for voltage. Is this clear, everyone? Is this clear, everyone? Okay, moving ahead. Yeah. So moving ahead, power dissipation. This is called the RMS value. Like I tell you what is RMS value. This is called RMS value for the alternating current. For simplicity, also in our household voltages are specified by their RMS value. For example, the 230 volt rating is the RMS value. Its peak value is 311 voltage. Why so? Because V.R.M.S is nothing but V naught, which is a peak value, upon root 2. Okay, so the value which is fluctuating for IRMS, or you can say for VRMS, is higher as compared to, I mean, RMS value. Okay, so this I naught V naught is going to be 311 volt, or as compared to the same in a same as, I mean, for the similar whatever the applicant you are going to use for you can say bulb or for refrigerator, for different electrical appliances, the IRMS and I peak value is going to be different. But in our household, this is the VRMS. So VRMS we are going to discuss, not the peak value, where V naught is peak value. Okay, is this clear, everyone? Okay, so this is your first question. A circuit has two resistors of this much ohm respectively. These resistors are connected in series. Find the expression for varying voltage across the 20 ohm resistor if the voltage source is given by this. Okay, see, this is your V equals to V naught sine omega t, right? Instead of omega, you have 20. So omega value is 20, nothing more than that. There is a circuit. In the circuit, there is a resistor 20 ohm. There is a resistor of 30 ohm. You need to find the what? Expression for varying voltage across 20 ohm resistor. Do that. Okay, first of all, find the value of I, and then from the value of I, uh, when you have R, so you can get the value of resistor, I mean value of voltage at any particular resistor. Okay, is this clear what I'm saying? The simple thing is, suppose this is your circuit. Okay, suppose this one is your circuit. In this particular circuit, one is one is this. Means this particular resistance is 20 ohm, this particular resistance is 30 ohm. 20, 30 ohm. Here you can apply a voltage which is this one. V equals to 10 sine 20t. Okay, so total resistance is simple, R total, because it is connected in this. So with this total resistance, find I value, and that is very easy because it is a resistor, nothing more than that. And when you have I and then when you have R, so at any particular the voltage is going to be different. Clear now? Okay, if it is in parallel, so the voltage is going to be remain same, then the current is going to be different. Did you understand this thing till now? If it is instead of series, it is given in the parallel, so without a doubt the voltage is going to be remain same. You don't need to calculate even single thing there. Is this that much hard? It is very easy, beta. Seriously, you take that much time for this? I don't know how you are doing in any exam. That this is very easy, beta. See, correct answer is B. I'm not going to wait that much now. I already teach you extent, then you are taking more time as usual. The total resistance is 50 ohm. Using Kirchhoff's law, V equals to IR. I is simply nothing but V by R. R is 50. So 10 upon 50, 0.2 negative. So this is your current. Okay, equation 1. And we need to find the voltage at 20 ohm. Or you can say V1. So that is nothing but I into R1 simply. And that is B answer. Clear everyone? Is this clear now everyone? I don't know what you are doing here. Okay, the next question is this. At what time from 0 the alternating voltage becomes 1 by root 2 times of its peak value? You need to find the time period. Tell me. IAC is 1 by root 2 times of its peak value. And you know the IAC. IAC is nothing but I root 2 sine omega t. So this particular t you need to find. Do that. Tell me the answer. I want to see how much you take time for this also. See, exactly. Okay. So by using V equals to, as you can see, by using V equals to V naught sine omega t, V by root 2, V naught sine 2 pi capital T upon T. Comparing this 1 by root 2 because V naught cancel. So 1 by root 2 is sine pi by 4, sine 2 pi by T. So sine cancel this thing, terminology, and this in this way you can get this simply. Okay. Now phasors. Like I already give you the example and everything about phasors, but in general, what are the phasors? So phasors analysis is used to determine the steady state response to a linear circuit functioning on sinusoidal source with frequency f. Phasor analysis computes only the steady state behavior. Now what it is, like in simple terminology you can understand, in AC voltage or current, my current or voltage fluctuating in this way. When I apply this particular fluctuating voltage to any particular circuit, how my circuit behaves in simple terms. This there is a 2-3 diagrams you are going to see. Like in any particular case, the voltage is going ahead as compared to the current. In any particular circuit, specifically in inductive circuit, voltage is going ahead as compared to the current. In capacitive circuit, the current is going ahead. Ahead means, suppose here it is your voltage. It starts from this. Okay. So current is going to be start a little bit lower, or you can say this little bit lower is basically pi by 2, because now you can see this is a cos value starting from negative 3, isn't it? Clear everyone? It is a cos value starting from negative, so it is going to be for inductor, and you are going to see in a minute also. For capacitor, if your voltage is starting from here, okay, this is your voltage, so the current is going to be started from this, and this is your phasor, I mean phase difference. The red one is current. Now this is for capacitive circuit, for basically capacitor, capacitive circuit, okay, or basically capacitor. So these are the basically phase difference we are going to observe. So the circuit should be linear, which means it is constructed from linear components like simple resistor, capacitor and inductors. A sine wave has three characteristics: amplitude, phase and frequency. So this angle, because it is a voltage, so as you can see this is cos, not sine. If I am going to find this, you can say current in inductor, because current in inductor is basically what? This is your e.m.f voltage, or e.m.f voltage is I mean this we have now e.m.f voltage E equals to minus L di by dt. Clear? This I have one relation, and one relation I have this. So if I am going to find the current with respect to this is my e.m.f voltage. So from here you can get simply di equals to minus 1 upon L E into dt, where my E, or which is basically V, is cos omega t. Clear? So I need to do the integration. I on inductor, I am going to write L. 1 upon L integration 0 to complete cycle t. You can say V naught cos omega t plus phi and then dt. Automatically you can get this. Okay, so this is basically happening here. Is this clear everyone? Just turn on your cameras, beta. I need to say this, I don't know, like you are a kid of 3rd or 4th class. So this is in general the difference. As you can see, VLM. VLM is basically the voltage for inductor. It is going to be ahead, and this is your phase angle. Okay. VRM is basically the voltage for resistor, and VCM is basically the voltage for capacitor. So phasor diagram somehow look like this. The properties of phasor: the length of a phasor proportional to the maximum value of alternating quantity involved. It can be voltage, it can be current, it can be anything. The projection of a phasor, this is the projection. This thing is gives you projection. This is the projection. Okay, this is the projection, and this is the projection. Okay, it is, this one is for capacitor, this one is for inductor, and this one is for resistor. Because for resistor, for resistance, the voltage and current remain same. Okay, and this one is your maximum voltage. This one is your maximum voltage. So for resistor, the maximum voltage and current remain same. For capacitor, voltage lags behind, and for inductor, the voltage is going ahead. So the projection of a phasor on the vertical axis gives the instantaneous value of the alternating quantity, means at any particular instant how much the quantity is involved. So that is we get from the phasor diagram. Is this clear, everyone? This is important also, a very important. Okay. Now this is impedance of a AC circuit, and we can skip it also, but in general I'm going to teach you. We are going to discuss this in great detail. Impedance is nothing but when we have more than one component. For example, LR circuit, CR circuit, or LCR circuit. Okay, LCR circuit in series we are going to discuss in the next. So the total resistance, the total oppose is known as impedance. For inductor is, for inductive circuit, it is impedance is known as inductance. For resistive circuit, the impedance is known as resistor. For combination, it is known as inductance. So every component used in the circuit has an internal resistance. Fair enough. That depends on the material used for the component. Resistor, inductor, capacitor, circuit. The R.M.S voltage is given by the formula V.R.M.S Z equals to I.R.M.S. In simply, what here we trying to do, wait, here I can draw. Suppose this one is one of my circuit. Okay, in this particular, wait a minute, this. Okay, so suppose here I can apply resistor, here I can apply inductor, or here I can apply. So this I have three components, and in these three components I apply my alternating voltage, which is V.R.M.S, or you can say V simply V naught sin omega t. So the total resistance, the total oppose is given by the Z, and this Z is impedance. In general, you are going to discuss, we are going to discuss the LCR series circuit. But if you want to, so in chapter assessment, I am going to give you the parallel also. So this impedance, where Z is the circuit's total resistance, this circuit total resistance. In an AC circuit, the circuit resembles, the circuit impedance is given by the formula, which is R square XL minus XC, where XL, what it is, omega L, or XC, what it is, 1 upon omega C. I teach you this thing in the previous class also. XL is the impedance of the inductor. Okay. And XC is the impedance of, basically resistance, or you can say impedance. Impedance of L. L is inductor. In the same way, impedance of C. I'm going to write. Impedance is beta, basically what it is, impedance of C. Okay. So in total, where XL and XC is the inductive reactance, you can say in this way also, capacitive reactance. XL, XC, and Z are all measured in ohm, same as the resistance, nothing more than that. Okay, so there is one simple question. The phase difference between the alternating current and voltage represented by the following equation. I equals to I naught sin omega t plus E equals to E naught cos omega t plus pi by 3. So tell me what is the phase difference. Now you are going to compare only and only when it is cos and it is sin. So either both are cos, either both are sin. And I give you the relation between cos and sin also. So find it down and tell me the answer. You need to convert one into another, either sin into cos or either cos into sin. It's your choice. Okay. When I tell you cos omega t, or you can say cos theta, is nothing but either sin pi by 2 plus or either sin pi by 2 minus. Are you getting or not? Okay. So do that. D. Exactly. See, I equals to I naught sin omega t, E equals to E naught cos omega t plus pi by 3. So sin pi by 2 plus theta also gives me cos theta. So instead of cos theta, I can write this. pi by 2 plus omega t plus pi by 3, which is pi by 6. Now I can compare because this equation A or this equation B both have sine component or sine function. Okay, you can write as a note to find phase difference, to find phase difference phi the current, or you can say the AC and AV, alternating current and alternating voltage, have to be in same trigonometric function, in same function. You cannot compare sine with cos or tan with cot. Is this clear now, everyone? So this is your correct answer. Is this clear, everyone? You need, I mean, obviously you are going to compare with one with another if all the properties, qualities are same. Clear? And that is why humans are not congruent, or we are not compare one to another. Like we hear this terminology so many times, you need not, you did not need to compare yourself with any other, because every human being have some certain qualities as compared to other, higher or lower also. We all are similar, not congruent. That is the one thing, or not identical. You can say that also. Okay, this one is a 12 omega resistor and this one Henry inductor are connected in series to an AC source operating this much cycle. The phase angle between the current and voltage is. Okay, I don't teach this thing, so I can explain this. See, given resistor this, inductance L is this, omega is 2 pi f, because I think frequency is given. Because it is operating at this much cycle per second. Cycle per second is basically frequency. Okay, and for this circuit, this is, we are going to discuss about LR or CR also. But in general, what is happening here, this is my resistor and this is my inductor, and this one is my voltage. If it is given, it is given or not? No, it is not given. But suppose it is any particular voltage, V equals to V naught sine omega t. Okay, now everything is given. So resistor R is given 12 ohm. This much is given 0.21 Henry. Okay. Now, obviously F is given, which is 50. Operating voltage 20 volt. Okay, voltage is given also. So V naught is given 20 volt and frequency is given 50 hertz. So obviously we can find omega, which is 2 pi f, and with the help of omega we can get inductive reactance, which is omega L, and in a similar fashion Z, the total impedance for this LR circuit. This is your LR circuit. For LR circuit, Z is nothing but under root of R square plus XL square. This is in the denominator. XL square. Putting the value, we can get the answer. Okay, so this is your net resistance. This is, now we get only impedance. Obviously, in the next, we are going to find the phase vector. So, but a phase, or you can say power factor, there is a formula to find the phase angle. So, power factor is defined in R by Z. Okay, and with this, you can get this important relation. In any particular circuit, either it is LR, either it is CR, LC circuit behaves in a different way, but for LR circuit, but for RC circuit, okay, no. For LR and RC, okay, or LCR circuit, the power factor which is defined as cos phi. Here phi is phase angle. Z is net impedance. Okay, or you can write it down here. Phi is phase angle. Clear? So in this way you can find phase angle for any particular thing. Now what it is saying, as you can read it out here, phase angle phi, which is cos inverse this one, 79.70, which is lagging phase angle between current and voltage source. So what is the meaning of saying this? Just give me a minute. I can draw for you guys. Suppose this is my voltage. What is my voltage? Just a minute. This is my voltage drawn. Whatever the voltage is given. Okay. So for this LR circuit, the voltage is going to be this, and the current is going to be this. And this particular angle, this particular angle between the voltage and the current, it is somehow almost 80 degrees. Okay. I make almost, not accurate. It is 79.70, so I can write 80. Is this clear? So that is the benefit of this particular thing, which is phase diagram, or this is known as your phasor diagram. Is this clear, beta? So in this way you can write it down. Okay, moving ahead. Now in a same fashion, like when I apply this particular voltage, AC voltage to the resistor, in a same fashion I can apply to the AC voltage for inductor, or you can say for inductance, a loop in general, or for you can say capacitance. But we are going to see the phase difference different. We are going to see the I is not having the same sinusoidal function. It is going to be cosine. Clear? In a minute you are going to see. Now you can see the same thing, everything. An inductor is connected instead of resistor. Now we are connect inductor, and inductor is connected to an alternating voltage source denoted by this, you can say this symbol. Assuming that the resistance is in the windings is negligible, as current changes in the inductor acquires potential, the circuit is a purely inductive circuit. Purely inductive saying that it is not connected anything else. Again using Kirchhoff's law. So Kirchhoff's law, V equals to minus L di by dt. Why? I mean from here this, I mean from where this equation comes. See, this is your voltage, or you can say any particular voltage which is going to be applied, or you can say alternating voltage we apply. And here there is a EMF is going to be generated, and better this EMF which is going to be generated at this particular inductance is nothing but this minus, or you can say L di by dt, minus L di upon dt. And what we know, according to Kirchhoff's law, the total voltage, which is V plus EMF, is 0. Right? V plus EMF is going to give me 0. This is my Kirchhoff's law. KVL, total voltage, total potential difference across a circuit. This is my circuit. Across a circuit is 0. Clear that? So I put it down in this way. V minus L di by dt. The second term in the equation is the self-inductance, and you can say self-induced EMF inside the conductor. Let the inductance be denoted by L. Then di by dt, instead of V, we can write Vm sin omega t. Again this V can be Vm, not mean value, maximum value, sin omega t. Okay, and then this. This is an equation in terms of current. It is expressed in terms of derivatives. So the slope, or you can say total, and I mean to find this particular, we need to integrate both the sides. The moment we integrate, or you can say di is nothing but 1 upon L. I already told you this equation even, sine omega t dt. Integrating from 0 to t, we can get this. Okay. I is nothing but Vm upon omega L. Omega L is what, beta? Omega L is Z, impedance, reactive, inductive impedance. Okay. So Vm by L, which is omega L cos omega t plus C, and this C is constant of integration. Is this clear, everyone? That is nothing but constant of integration. Mathematics right now I'm doing. So thus the value of constant is 0. Why? Because initially my current or voltage is 0. So I equals to Vm by omega L cos omega t. Rearranging the above term, why should I rearrange? Because my V is in terms of sine. To find the phase difference, I need to rearrange into the sine term. So I, which is Vm upon omega L, instead of cos omega t, I can write sine omega t minus pi by 2, right? And that is how I can see my I, which is current, is lagging behind. Here I am Vm by omega L. It is the amplitude of oscillating current. It can also be rewritten as Im. I can directly write Im sine omega t minus pi by 2. Is this clear, beta? And Im is nothing but this one. So moving ahead, this is my Im is Vm by XL. You can write it down in this form also. And again the power and everything, we are going to find it down on this. Okay. So what basic thing we are getting from here? The same diagram I drawn here. Clear? This is your diagram you are going to observe here as well. Okay, instead of 80, I can write it down 90 there. So here you can see the same thing we are going to, and that is my phasor diagram. Now instead of 80, it is 90. Nothing. Okay. Because you can see this is your voltage of inductor and this is your current of inductor. Clear, everyone? And it is almost 90 degree. So that is why I can write voltage current is lagging. Current lagging by current lagging behind current lagging behind by voltage by pi by 2 in LR circuit. Sorry, in inductive circuit. Clear? Lagging behind by pi by 2 with respect to voltage. I'm not going to rewrite everything again and again. You can understand. Is this clear, everyone? Is this clear, beta? Everyone? Okay. So now this is simple. Im, we can write Vm by XL. XL is omega L. I write it down. Now in the same way, as you can see, this is the phase diagram for sinusoidal thing, because you can see in general my current is going to be cos, and that is represented by here as well, because it is a cos function, right? If I'm going to see with the 0, so this one is my voltage, which is Vm sine omega t in general, and this one is my current, which is im cos omega t in general. But to convert cos into sine, I can write im sine pi by 2 minus omega t. I can treat omega t as a theta. Simple. Clear? So the power dissipated in a purely inductive circuit can be derived by using instantaneous equation of power, that is PC is IV and Im sin omega t minus pi by 2 into Vm sin omega t. And you can see that sin omega t cos omega t is nothing but multiplying and divide by 2, you can get 2 sin omega t. That is going to be above. Okay, this is wrong. Wait a minute. The actual formula is, if I am multiplying and divide in this above equation, suppose this is your equation number 1. So if I am multiplying and divide 2 in the sine equation, so I can get minus of Im Vm divided by 2 into 2 cos omega t sin omega t. Okay, and this is nothing but power average, simple power, instantaneous power Pi is minus of this Vm Im divided by 2 into sin omega 2 cos omega 2 sin 2 theta. Sin 2 theta is 2 sin. From here I can write it down. So this is my instantaneous power, and obviously average power is 0 because it is sine function. So for sine function, average power for complete cycle is 0 because I already write, instead of theta I can write 2 theta. Instead of 30 degree I can write 60 degree. Simple. Clear na everyone? Clear na? But the same thing is sine again. So that is why power, average power dissipated in this case is 0. Why it is 0? Because instantaneous power is V maximum I maximum divided by 2 sine 2 omega t. Clear? Okay. Good. Moving ahead, this one is your question, find the answer. And then after this particular question, the main thing is remaining a voltage applied to capacitive reactor. So sorry, capacitive circuit. In the same way we can find the current, in the same way we can find the phase difference, in the same way we can find the power average and everything, and then 2 questions. We can do that in next 20 minutes. Okay, so what it is given in this, the current and voltage in an AC circuit respectively is given by I equals to sine omega t and E equals to sine omega t plus pi by 3. Phase angle is given. If the resistance is this much, then the reactance of the circuit. You need to find the reactance. So how we are going to discuss? From the given equation, I equals to this, V naught equals to this, Z equals to V naught by I, total impedance, right? And we know that Z is square equals to, Z, how you can find Z? R square plus XL X square, because it is an inductive reactance. LR circuit, or you can say inductance there. So in this way you can find inductance. Okay. Simply total impedance is always V naught by I naught. And then using this we can get it. B answer. B 100 root 3 omega. Okay. Clear everyone? Now when 100 volt DC is applied across a solenoid, okay, a current of 1 ampere flows in it. When 100 volt AC is applied across the same coil, the current drops to 0.5 ampere if the frequency of AC source is this. The impedance and the inductance of the solenoid are. Okay, tell me this one. Voltage is given, current is given. So you can find the net impedance with this, and then the same thing is going to be repeated. Do that. Take your time. Okay. From the impedance, from the DC thing you can find the resistance. From AC thing you can find the total impedance Z, and then again using this z equals to under root r square plus xl square. Xl is nothing but 4 pi square f square omega square l square. You can get the L and tell me the value of L. See, after this I'm going to wrap up in next 5 to 10 minutes. I'm not going to repeat everything again and again. Instead of inductor, I'm going to use the formula of capacitor, and in capacitor v equals to we know something which is charge equals to CV, right? And with the help of charge, which is dq dq by dt, I'm going to differentiate it. That's it. And within a fraction of seconds, you are going to understand also. But tell me the answer of this one. You have DC voltage, you have ampere, so from there you can find the resistance R. We have you can say AC voltage or AC impedance, current. So from there we can find Z directly, total impedance, and then we can find R and L with the help of Z square equals to R square plus XL square. XL square equals to 2 pi F omega square L square. Omega square is 2 pi F to the power 2, which is 4 pi square F square. Maximum 1 minute more I can give it to you. Tell me the correct answer, beta. Tell me which one is the correct, beta. C. How C, beta? The correct answer is A. Okay. No, A. Yes. I am not getting this answer. Why, beta? How many times I need to explain? Okay, C. It's okay. Not a worry. See, DC applied. So I equals to V by R. Okay. That is 100 ohm. When AC is applied, so I equals to V by Z. 0.5 100 upon Z. It is total impedance, not simple impedance. So Z equals to 200. So using this R square L square, you can automatically get this 0.55 ampere. Clear? Because it is current and it is source, or you can say frequency 50 hertz. This sometimes also known as frequency. Even it is in colleges and in your maximum books you find frequency in this way. Okay. Is this clear, everyone? Okay. So moving ahead, now I'm going to tell you this direct thing. As we know, in capacitor Q equals to CV, and I want to find my current, which is I, which is dq by dt. From there I can get the current in this circuit. Okay. Here I'm not using this particular voltage thing in an if. Yeah, even if I'm finding this voltage on this, so this formula I'm going to use. Here na, in any particular capacitor, charge is this. So from there, voltage on capacitor is nothing but C upon Q. From there we get the this thing. So an AC voltage source is connected to a capacitor. The expression of the voltage from the voltage source is V equals to Vm sin omega t. As capacitor is an electrical device that stores electrical energy, it is a passive electronic component with two terminals. The effect of the capacitor is known as capacitance. Okay, using V equals to Q by C. Same thing. Using V equals to Q by C at a particular time, T denotes the charge. on the capacitor by Q. The instantaneous voltage across the capacitor is this, V equals to Q by C. The same thing, Q equals to CV or VC, whatever the formula you need to remember. So using Kirchhoff's law, Vm sin omega t equals to Q by C. Again, because it is discharging and charging, so this Vm minus this Vc is 0. So Vm is Vc, voltage on capacitor, which is Q by C. Clear? Now I need to find the time, I need to find this particular current. So I, which is dq by dt, simply I am doing this. Since the current is continuously changing, to find the current, derivative of the charge is required. So differentiating the given equation, this given equation, you can make equation number 1. So differentiating equation number 1, we can get d by dt of Vm sin omega t, which is d by dt q by c, 1 by c dq by dt. This is my I. Okay. So Vm omega cos omega t is I by c, and then Vm omega c is cos omega t. So as we know, Im is Vm omega c cos omega t. But to get, it is not Im, it is I. Okay. This is the general equation. But Im is nothing but Vm by Z, impedance on any particular circuit. So here the impedance is capacitive. So the capacitive reactance is nothing but 1 upon omega c. This way you can do that. Okay. So this result is rearranging the above terms. I equals to Im sin omega t plus pi by 2. Im is Vm omega c. It is the amplitude of the oscillating current. It can also be rewritten as this. Why should I rewrite this? Because Im is nothing but Vm upon Z into C. So if I put ZC, which is capacitive inductance, or you can say capacitive impedance, 1 upon omega C, I can get this. Okay. Is this clear? Instead of this. Wait. This is Vm upon ZC. The moment I put ZC equals to 1 by omega C, I can get this terminology again. Is this clear? So I don't write automatic like ZC equals to 1 by omega C or ZL, which is omega L. This is the, you can say, finding with the help of differentiation integration formulas. I'm not rewriting by myself. Okay. This equation, when compared to the Ohm's law, is gives 1 by omega C as the resistance. It is called the capacitive. It is called the capacitive reactance, and it is denoted by Xc. So now amplitude of the current becomes Im, which is Vm by Xc, and this Xc, or you can say Zc sometimes. Okay. Simple. Now you can see here the voltage is this one, V equals to Vm sin omega t, but current is this. This is my current, and this current is I equals to Im cos omega t. And to write cos into sin, I can do that. Sin omega t plus pi by 2, because I is ahead as to this. So here what we can understand, in purely capacitive, capacitive circuit, voltage lagging behind, by pi by 2 with respect to conductor, with respect to current, or you can say with respect to alternating current. Is this clear? Like in inductive circuit, the current is lagging behind. Lagging behind means it is below, or it is behind as compared to the current. Clear? As you can see, it is ahead. Current is ahead in this capacitive circuit, where voltage is ahead in inductive circuit. And you can uh, understand on the terminologies of lagging behind. Here voltage is lagging behind or in inductive circuit current is lagging behind. So simply the phase difference is pi by 2. The figure given below shows the variation of voltage and current with the time. The power dissipated is a purely capacitive circuit, can be derived by using instantaneous equation. Again, instantaneous power is IV, you can put it down, and then same thing, sin omega t pi by 2 cos omega t, multiply and divide, you can get the same terminology. PC is, okay, instantaneous power is I.m.V.m sin omega 2 cos omega t, multiplying and divide by 2, the same thing we can get. Instantaneous power is I.m.V.m by 2 into sine 2 omega t, because this formula 2 sine cos omega 2 sine theta cos theta is sine omega t. So this equation is again not correct. Vm Im upon 2 sine 2 omega t. Okay, and how it comes from this particular formula simply. So the average power dissipated in this case is always also 0. Clear everyone? Now we can find few questions. The frequency for which a 5 microfarad capacitor has a reactance of this is given by, see, this is your XC is 1 upon 100 ohm and C is 5 into 10 to the power minus 6 farad. Now what you need to find? Frequency. Clear? Frequency is omega. Frequency is omega upon 2 pi. So find omega from this and then frequency. I don't think so the easy question from this related to this subtopic or topic. Tell me the correct answer now. Tell me beta. Okay, tell me this quickly. Meanwhile, I can see your assessment from this. Wait a minute. Self-assessment I need to see also. This is your AC in AC. This is your questions. Okay. Easy questions are there. Tell me the answer. B, A. Anyone say any other? C or D also someone? A, if I'm not wrong. Sir, this is very easy. I don't think so much easier than this. Okay, try this. This one is a little bit tricky. A capacitor of 10 picofarad is connected to a voltage source is given by this. This is V0, this is omega. Find the amplitude of the current. See, nothing is hard here as well. Omega is given, right? And C is given. So you can find XC, which is 1 by omega C. And then with the help of this XC, you can find IM. Got it? Is this clear? And pico is Do this and tell me the answer quickly, and then try your this CA also. XC find, and then IM you need to find. Very easy. D. Exactly. The correct answer of this question is D. I hope and I believe everyone get it. See how you get it? Simply, you need to find IM, no? IM, which is VM upon XC, and which is directly 50 into omega into C, simply. Because XC is 1 upon omega C. Do that. So 50 into 10 into omega is 20. So doing that you get the answer D. But here I don't know why they find XC first. There is no use. I'm telling you. Put it into the direct formula. IM, which is VM upon XC, or directly omega C VM. Everything you have. Omega you have, C you have, VM. Directly put it into the formula, you get the answer D. Okay. So now the main important things in this particular lecture we are done. Introduction of AC and types of AC and voltages applied to the resistor. Representation of AC, or you can say current and voltage by phasor. Alternating voltage, or you can say current applied to the inductor or capacitor also. Okay. So this is the summary.